Hi guys. Okay, so we're going to try do the AS level questions. Sorry it's taken me so long. I kind of have to wait till this time not to have builders buzzing. I think it's like 4 a.m. or something. So let's have a look at the first set of topic, which is the proof questions. Okay, so question 1 says you want to show that x squared minus 8x plus 17 is greater than 0 for all real values. Now, whenever you see a greater sign anywhere with a show that, your brain should go, complete the square, complete the square, complete the square. So let's complete the square, and that's going to prove it to us. So if we have a look, we've got half what's in front of the x. So if you forgot how to complete the square, I think there's a separate video on that. Square that number, and then you've got the add 17. So when we do that, that's equivalent to x minus 4 squared plus 1. And then we just need to make a comment. Now that's definitely going to be greater than 0. So you're going to say x minus 4 squared is greater than or equal to 0. Well, that's a fact because it's a square number. You don't need to say more than that. Therefore, x minus 4 squared plus 1 must be greater than 0. It's actually greater than 1. So x squared minus 8x plus 17 is greater than 0 for all real values of x. So to show that with a greater than, it's more than 2 marks. That's also your clue. You're doing a bit more than plugging numbers in, which leads us on to the next bit, where you've got, if I add 3 to a number and I square the sum, the result is greater than the square of the original number. So here I'm actually, number 1, it's only 2 marks. That's your clue that you're probably just going to plug some numbers in. And when you're plugging numbers in, typically it's the sometimes true. That's a good kind of place to go. But let's try it. So let's pick a number. So I'm going to add 3 to a number. I'm going to pick any number. Let's say let x equal 6. I'm going to add 3 to the number. So 6 plus 3 equals 9. So 6 plus 3 squared. And that gives me 81, which is greater than 6 squared, which equals 36. So when x equals 6, it's true. Right, now let's try, well, we know the difference would be potentially negative 6. So let x equal minus 6. Minus 6 plus 3 gives you minus 3. And then you're going to square it, gives you 9, which is not greater than minus 6 squared, which is 36. So not true, therefore sometimes true. Because it works for some cases and doesn't work for others. So the clue is in the fact it's 2 marks. And then on top of that, you've got sometimes true as your option. Okay. Right, next question. Use a counterexample to show that the following statement is false. So here's where you've just got to read the question carefully. A lot of my students didn't appreciate that we only want numbers between 3 and 10. You literally can just plug it in. So I'll start with 3. 3 squared is 9. 9 minus 3 is 6. Minus 1 is 5. That's a prime number. Let's try 4. 4 squared is 16. Minus 4 minus 1 gives me 11. It's also a prime number. So you can go through this process, plug in your calculator, use the equation button in the calculator. Doesn't matter how you do it. And you end up finding that when you get to let n equal 8, you get 8 squared minus 8 minus 1 gives you 55. And you'll say 55 is equal to 11 times 5, therefore not prime. And there's your counterexample. prove that, and also, again, plugging numbers in, the clue is it's 2 marks. You're not going to be asked to do loads with it. Next bit, prove that the following statement is always true. So when something's always true, we can't just substitute numbers in. We've got to use some algebra. The difference between the cube and the square of an odd number is even. Okay, so let's go back to basics. Whenever we talk about proofs, and this was what you would have learned in GCSE, but I know we forget these things. So whenever we're talking about proofs, whenever we're considering an even number, we're thinking of it as 2n or 2x. So that's your even. Now, an odd number is always an even number plus 1. So if we're thinking of an odd number, we think of an even plus 1. Now, there's 2 ways to do this. I'm going to show you both ways in case, you know, whichever one works better with your brain or how you think about even and odd. So we want the difference, so we know we're taking away. So the cube, so we're going to have 2n plus 1 cubed minus 2n plus 1 squared. And now comes the fun bit of opening it all out. Now, when you open it all out and clean it all up, you end up with 8n cubed plus 8n squared plus 2n. Now here you can take a factor of 2 outside the bracket. Now the minute you can do that, you know it's an even number. Plus 4n squared plus n, which is even. Now I think that's the way that will always work. Think about your even numbers, your odd numbers, and you can work through it like that, and that should make sense. However, if you prefer and you're happy with even times even, odd times odd, etc., you could think about it like this. You could say, let number be n, let odd number be n, and we've got n cubed minus n squared. Now we can factorize that, and we know this is an odd number. N, we can take n squared outside the bracket, n minus 1. We know that n squared, so this is an odd times an odd multiplied by an odd number minus 1. So an odd number times an odd number is always an odd number. And an odd number take away 1 has to be an even number. So we end up with odd times an even, which equals an even number. And that would be another alternative proof which you could use. Right, next question. Proof for all positive values. Okay, so the key here is positive. Now, when there's positive values, when we multiply or divide by them, it doesn't change the sign. That's the important bit. The minute it ends up being negative, potentially changes the sign when, well, it always changes the sign when you divide or multiply by a negative number. Okay, so positive values, and we've got an inequality, we know the sign's not going to change, no matter what we really do to the numbers. Okay, so proof for all positive values, this is the case. So I look at that and go, oh, that looks a little bit strange. I'm going to multiply the 2 up. Not really sure what I'm doing yet, but it's only 2 marks. It can't be too tricky. I'm going to multiply the 2 up. So is x plus y. And then I'm going to put everything on one side. So I'm going to move this onto that side. I get x minus 2 root xy plus y greater than or equal to 0. Now that whole something bigger than 0 is probably something to do with completing the square, or I can have an exact square. So can I make this something exactly squared? So what I do is I look at the first number, this one here, and I take the square root. And then I look at this last number and I take the square root. So if they were squared, and if I put a minus sign, because there's a minus sign there, if I was to open that out, I'd get what was above. So you'd say that is greater than or equal to 0, and you're done. So that's your proof, because you've shown that it can be squared. But only when it's positive am I able to do that, because the square roots in this case would be real. So positive values, therefore square roots are valid. Remember, it's illegal to take the square root of a negative number when we're in normal maths. Prove by counterexample this is not true when x and y are both negative. Counterexample, just pick some numbers. So let's pick some numbers. Well, let's let x equal -3, let y equal -5. My left-hand side becomes -3 times -5, which gives you -3 times -5, which equals 15. So square root of that, so root 15. And then the right-hand side becomes -3 plus -5 over 2, which is -4. And root 15 is greater than -4, so result not true. Okay. All right, so those, it's only 3 marks. If in an exam you're having a panic, move on, leave the 3 marks alone. You know, you can even get full UMS with 3 marks. Okay, given n is a natural number, prove that n cubed plus 2 is not divisible by 8. Okay, so we're looking at this and you're like, it doesn't tell us whether it's even or whether it's odd. So what I would do is consider both cases. I'd say if it was even, what happens? And if it was odd, what happens? Now you can do it logically using if n is odd, then this happens, and if n is even, or you can use it using algebra. So we're again going to do it both ways. So let's take it algebraically to start. So if you like, this is your algebraic version, and then we've got a logical version. Right. So if n is even, n equals, let's say, 2k. So we're going to get 2k cubed plus 2. 2 cubed is 8. So we're going to get 8k cubed plus 2. And we're going to say this is 2 more than a multiple of 8. Therefore, not divisible by 8. Because if we divide it by 8, we're going to have 2 as a remainder. And if n is odd, 2k plus 1 cubed plus 2. And you're going to open that all out and you'll get 8k cubed and so on. 12, and then you'll get 12k squared plus, and yeah, 12k squared plus 6k plus 1, and then you add the 2, so you end up with 8k cubed plus 12k squared plus 6k plus 3, right? Now all of this is even plus 3, which is odd, therefore not divisible by 8, because an odd number can't be divisible by 8. Okay, so that's your algebraic approach. Now your logical approach would be, if n is even, we know that n cubed is a multiple of 8, because an even number is a multiple of 2, therefore n cubed is a multiple of 8. So n cubed plus 2 can't be a multiple of 8. Okay, and if n is odd, that means n cubed is odd. So an odd number plus 2 is odd, because an odd number plus 1 is even, therefore can't be a multiple of 8. Sorry, that's just copying it down, being lazy to write. So hopefully that makes sense. So you've got 2 options. It doesn't matter which way you do it, you would get full marks, but it depends sort of how your brain works. Generally, if you can't think of these things, go with the algebraic approach because it'll always work. And you don't have to worry about even times odd and, you know, so on. Right, question 5. Prove that for positive values a and b, 4a plus b over a is greater than. Again, we have positive values. There's no square roots, so we're not worried about the square root bit, but we can think about the sign. And then we've got a counterexample when this was potentially not true. But it doesn't say they both have to be negative. One could be negative, one could be positive. Okay, so I would look at that and I'd be like, okay, well, we're thinking about positive values, so we can just multiply everything by AB to get the AB on the top. And so I would multiply, everything by AB to start with. So when I do that, if I multiply 4a by AB, I'm going to get 4a squared. So I'd probably put multiply by AB. So I get 4a squared plus b squared is greater than or equal to 4ab. Stick everything on one side again. And again, it's the same thing. If you want to do an exact square, and the clue is it's a proof question, it's leading you that way, you take the first value and you square root it. So 4a squared, square rooted gives you 2a. The last one you square rooted, you get b, and you can put a minus sign, and you just double check. If I was to open that out, do I get the minus 4ab? Which I do. So you'd say 2a minus b squared greater than or equal to 0 for all positive values. And then you'd say therefore, and you'd rewrite that. Therefore, 4a over b plus b over a is greater than or equal to 4 for all positive values. Okay, so prove by counterexample this is not true for all values. Right, so we know we've got to include a negative somewhere here. So let's, I'm not sure what one works, so we're just going to pick some numbers and see where we go. Right, so if we say for part B, let A equal, what we want it to be greater than or equal to, there's not true, greater than or equal to 4. Okay, so let A equal 6, B equal minus 1, I guess. So we're going to get 4 times 6, so 24 over minus 1 plus minus 1 over 6. So yeah, that works. Anything with a negative, so we're going to get minus 24 minus a 6, which is less than 4, therefore, therefore not true for A equals 6 and B equals minus 1. Now you could have chosen anything that just makes it a negative minus a negative, because then it's definitely going to be the case. Okay, and I think that's the end of that one. Right, so I hope that one's useful. I'm just going to start now, and I've got a few hours, so I'll just keep working consistently through them. Hopefully we'll get through most of the AS ones today, and we'll see how we go. I hope that was useful.